conference reception. So, welcome.
Okay, hello everybody, thanks for attending this talk. My name is Duqu and I'm from the Crisis Lab, which is a research lab at the Budapest University of Technology and Economics in Hungary. The work which I will present is a joint work with some of my students and colleagues from the university. And also I should mention that the work was supported or funded by the Office of Naval Research Global. And I will talk about this work, which is basically a project in which we developed a repository of signed code, which we shortly call ROSCO. This work was motivated by the fact that modern operating systems usually require digitally signed system software, such as drivers and OS updates, before those are installed. So these digital signatures are checked before these software components are installed. And so in order to remain stealthy and not be discovered immediately by users, attackers also need to sign their malware. And we observed this maybe for the first time in case of targeted malware like Duqu, Stuxnet and Flame, where in each of these cases some digital signature were involved. In fact, in case of Stuxnet and Duqu, as you may know, they both use a kernel driver, which was digitally signed, and that signature was produced with a possibly compromised key of some Taiwanese manufacturers. In case of Flame, it was a little bit different, but also Flame included digital signatures. Flame appeared to be a signed Windows update, and the certificate chain, which was there for verification of the signature, actually chained up to the Microsoft root. So somewhere in the chain there was a fake certificate, in fact, which the attackers obtained in a fairly sophisticated attack that involved probably MD5 collision, finding a lot of MD5 collisions and things like that. There are more recent examples as well. So in 2013, or sorry, 11, the WinNTI group infected some players of an online game with some malicious game update, which was also signed. In that case, it was signed with a South Korean game developer. And later, probably the same group of attackers also attacked some South Korean social network sites or operators, again with a Trojan which was signed. In that case, it was a Japanese game vendor whose key was probably stolen and used for signature. And later in 2013, the same stolen key was used to sign a Trojan deployed against Tibetan and Uyghur activists. An even more recent example would be the Wild Neutron group, which actually carried out successful cyber espionage attacks earlier in 2013 against large companies like Apple, Facebook, and so on. But they returned back in 2015, this year, and they used a dropper in some of their campaigns, which was signed again with a stolen and still valid certificate or signing key that belonged to Acer, another manufacturer. And the problem with all this is that the standard signature verification procedure does not allow for detection of this kind of misdeeds. So basically we cannot detect compromised keys, and we cannot detect fake certificates with the standard verification procedures. In fact, imagine that if someone's key is compromised and he's not aware of that, so the corresponding certificate is not revoked, then anyone, I mean, the one who compromised the key, who stole the key, can use that key to sign, and no one will notice that. And similarly, a fake certificate, until the owner somehow recognizes that there is a fake certificate issued for his name, for example, and until it is recognized, anyone can use that fake certificate in any kind of attacks. So that was the motivation, and we set the objective of somehow augment the standard signature verification workflow, the procedures, with some additional services that would help to detect compromised keys, fake certificates, and hence to help to detect malicious software before it is installed. More specifically, we wanted to provide reputation information on signers and signed code. For example, we wanted to be able to respond questions such as, is this signed software known? What do we know about it? Is it a known malware, for example? How many other users requested information on this signed software? And most importantly, is this software has a known signer, and what else that signer signed before? What do we know about software that signer signed before? Another thing that we wanted to achieve is to be able to notify key owners when a new object signed with their key, with a specific key is seen, such that they can verify that it was really signed by them. So this would make possible to detect compromised keys and fake certificates relatively quickly by this notification. So we wanted to build a system that provides the necessary infrastructure and mechanisms for all these additional services. And here is a few two example use cases just to better imagine how this would actually work. So imagine that a user downloads a software from some software repository or some software store. In this case, in this example, it's an Android package. And in fact, this use case example based on a real example. So we indeed observed this software. We downloaded it. It was signed by a mysterious signer. The name was just Ivan, which obviously immediately was suspicious. So what the user could do, the user could check on VirusTotal what VirusTotal would say about this software. And in that case, it just said, 1/47 at that time. So it looked like it's not a malicious software. But now the user could go to the system that we want to propose and ask our system what else Ivan, this mysterious Ivan, has signed before. And our system would return a few other Android packages that have been signed by this Ivan. And then the user can check all these on VirusTotal, and those have a higher detection rate now. And it's very likely that, in fact, the first package which was downloaded, which had a low detection rate, was also malware. And it was just new, not yet known to the antivirus products. And that's why it has got such a low rating. In another example, a user would download a software package which is signed and some certificate is attached. Maybe it's a fake certificate, like in this example. So again, the user could ask the system, have we seen this certificate before? And let's imagine now that this software maker, who in this example Microsoft, registered a trigger, an alarm trigger in our system that whenever we see a certificate issued for his name, whenever we see some software which is signed with this particular key, we should notify it. So in this case, the alert matches. I mean, now we see a certificate issued for Microsoft, and we have this alert triggered in our system. So we would first of all send the user the response that we've never seen this certificate before, and at the same time we would notify the software maker that, hey, here is a certificate issued for your name, and now you can check, is this really a certificate that you issued or not? Or is it really your certificate or not? Okay, so the way we do this then is the approach is that we build a large database that can store millions of signed objects, software packages, and certificates. Basically, we store portable executable files, Java archives, and Android packages, and we also store public key certificates. And on top of this database, we provide services that allow simple queries for file hashes, but also more complex queries based on some object attributes. We also visualize the relationship of different objects in our database, so users can better understand who signed what and how all these certificates and software are related. And we have also an alert service by which we can alert users when the system encounters an object matching some alarm trigger. We provide a web-based and a programmatic interface to these services. So the database can be browsed through a web-based interface, but it can also be queried by programs through a JSON interface. And we massively collect signed software and certificates. We have crawlers that crawl the internet and public software repositories for new signed software and certificates. And we, of course, also allow for users to upload new signed objects. So this is how the system looks like. The heart of the system is actually consists of two databases. We store the big amount of data that we collect in a NoSQL database. It stores all the attributes of the signed objects and their relationships and references to the files if we also store the file. And we have a traditional SQL-based database where we store metadata on the signed objects and some other information related to user sessions and alerts. And we have uploads and feeds that we process. So basically, users, as I said, can upload an object through the upload interface, which is a web-based interface, but we can also process bulk feeds of signed objects, for example, malware feeds or whatever kind of other feeds. This input is processed by pre-processing modules, which we have for each object type that we collect. These pre-processing modules basically parse the objects and insert the appropriate data in the appropriate database. In addition, also, there is a connection to external malware databases, so we can immediately check if a file is actually a known malware, and then we can flag it and store it in that way in our database already. Then we have the query engine, which serves the interface. So we have a query interface, a web-based query interface where the database can be browsed. And we, as I said, we also have this JSON interface where programs can query the database. And all these queries are processed by the query engine inside, which takes the data, converts the high-level queries to low-level queries, takes the data from the database, and returns the response. And users can also define trigger conditions for alerts. So for this, we have a web-based alert interface, and then we have an alert engine which periodically looks into the databases. If there is an object which matches the registered triggers, it would send an alert to the users. We implemented this as a Hadoop cluster of 6 nodes at the moment. So we have one distinguished node, a name node, and 5 data nodes. Altogether, we have a 100 terabyte total disk space capacity, but we store everything redundantly. So the effective storage capacity of our system is at the moment around 30 terabytes. The NoSQL database is an age-based database, which is a distributed database. So everything is distributed across these 6 nodes. And as I said, this NoSQL database stores all the attributes and relationships between the different signed objects that we have. And we have a regular database which stores the metadata and so on. It runs on the name node. It's a MariaDB, and for managing all this infrastructure, we use the Cloudera manager. The object types that we collect, we collect certificates, X509 certificates. Actually, millions of certificates have already been inserted in the database. We acquire those certificates either by known available collections, for example, the SSL Observatory collection, but we also use our own ZMap scanner. So we scan the internet and we collect certificates that are available there. And of course, we also extract certificates from signed software, which is uploaded to our system. Those software, so for example, PE files might have embedded certificates in them, which we extract and store them as certificates in our system. We collect signed portable executables, exe files, and DLLs. We have thousands of those files already collected. We have active, proactive crawlers. We crawl public software repositories, for example, SourceForge and so on. And we also browse operating system distributions. And we have also malware feeds, so we filter malware feeds for signed malware. We also insert those into the database and flag them as malware. And we have signed Java archives and Android packages. We again crawl third-party app stores, and we have stored thousands of those files already. All these input or these different types of objects are processed by these pre-processing modules. Each object type has its own pre-processing module, and these parse the object. And actually, it's not such a simple operation, because during parsing and processing, a module might need to invoke another preprocessing module. For example, if the P file contains an embedded certificate, then the certificate would be processed with the preprocessing module, which is responsible for certificates. So it's a quite can be a quite complicated process, but it's doable. We also check for duplicates, of course. Duplicates might be there because our crawlers may return objects that have already been inserted in the database, but we detect these duplicates, and in case of duplicates, of course, we don't insert the data again, but we just update the metadata. And we also discover relationships. When we insert a new object into the database, then we look into the already existing objects, how this new object is related to those. For example, it is signed object, which we insert, is the public key with which we can verify the signature is already in the database. Or if it is a certificate that we are just inserting, does it contain a public key which we already know, and it is in the database. So all these relationships actually can be represented as a directed graph, where the nodes, there are three types of nodes: certificates, public keys, and signed software. And there are two types of edges. One type is a certificate public key edge, which would mean that the certificate contains that public key. And the other type of edge is a public key signed object edge, which means that the public key verifies the signature on the signed object. Here's an example. So for instance, we might have a certificate here, which is actually a self-signed certificate. So it contains a public key which also verifies it, but this public key also verifies this signature, this certificate here, which has a public key inside, which verifies all the signatures on all these APK files. And as I said before, we actually visualize these relationships in our user interface. So that's an example for that. Here, in fact, we can see that example I mentioned at the beginning. Here is this mysterious Ivan. So this is this 10, the yellow node is a certificate. It is this certificate issued for Ivan, and it contains this public key. It's also a self-signed certificate, so there is an arrow in the other direction as well. It's an RSA key, and these keys can be used to verify all these APK packages which have been signed by Ivan. And so we can visualize these relationships. Now, let's look at a little bit how this really looks like in practice. So if you go to our website, rosco.crisis.hu, you would find this user interface. Here are the main services that we provide: search, upload, and alerts. And all these services, as I mentioned, also available via JSON interface. So if you look at search, you can search for hashes, you can search for certificates, executables, and so on. I will only show you these three because of time. So for certificates, you can specify, first of all, the kind of attributes that you want to give as a search criteria. So these are typical X509 fields, certificate fields, and certificate extensions. For instance, you can add the issuer country as an example, and field that you look for certificates issued in Hungary, for instance, in this case. And then you push the search button and you get something like 6,000 certificates all issued in Hungary. If you click one of these, then you can see all the information that we store about this certificate. Basically, we store metadata, as I said. When this certificate was uploaded, when it was last viewed and how many users queried this certificate already. And there are some fields related to the certificate itself, you know, version number, serial number, and so on. And here maybe you notice that this is a kind of strange serial number, 1, 2, 3, 4, 5, 6, 7, 8. So you might be interested in, oh yeah, let's see, is there any other certificate with this kind of serial number? So if you push this button here, then this is added as a new search criterion immediately to the certificate search dialog box, so you can search again, and now you have just 8 certificates all having this serial number, and you can look at the data again. This is just one example. For executables, you can specify type, file name, timestamp, and so on. There's also this potential malware flag, so you can look for executables that we already suspect they are malware. For instance, you just specify a type of executable exe, so we find almost 4,000 executables currently stored in the database. And if you just select one of those, then you see again the metadata, when it was last viewed, queried, uploaded, some fields from the PE header, and the signature, of course, and some certificates that have been embedded in the PE file, and now you can click on those and look the details of the certificates as well. And here's this potential malware flag, which in this case is false, but we maintain this flag, so basically if the binary was obtained from a malware feed via some bulk upload, then we set this flag, and also regularly we go to VirusTotal, check the VirusTotal score of all these executables, and if it is above a threshold, then we flag it as potential malware. We can also look for public keys. Here we can specify type and lengths. For instance, in this example, we look for a really short key, like a 768 bits key, and interestingly, there are something like 50,000 such certificates that has this very short key, and if we look at one of those, that indeed we see this. And we can actually click on this link here, and we can go to the graph view, and we see that this public key, in fact, is contained in many certificates, which is a strange anomaly. Usually, one public key is contained in one certificate, and it turns out in this case it's a public key that is used by multiple devices, and they have all these certificates, but they all have the same public key, and potentially then they have the same private key. So if you compromise one of the devices, then you compromise all the devices. So that's kind of anomaly that you can discover with just browsing the repository. You can also set alerts. There are 2 kinds of alerts. You can set a trigger for specific, you know, for instance, in this example, you have an alert. Anytime we see a certificate which has this keyword in the name of the subject name, then we would send out an email alert, or we can also set an alert for signed objects. So if we see an object which is signed with a particular key, then we can send an alert. So why should anyone use ROSCO? First of all, for end users, there's a clear advantage or benefit, because ROSCO helps them identifying potentially malicious software. For signing parties, there is also an advantage, because they would be able to detect fake certificates or compromised keys if their key is compromised. It's also beneficial for software platform operators like operating system providers, because first of all, they are also signing parties, and second of all, if they provide data to the system, to the ROSCO repository, then they help maintaining the trust in their platform. Also can be very useful for security companies such as AV companies. This is an additional source of information about users, what type of applications they install, how they are infected by malware, and things like that, and also about signed campaigns that involve signed malware. They can get more information from the database. And for regulators and authorities, there might be interesting statistics that they can use when they define different defense strategies. There are also some potential limitations. The database is a central system operated by a single entity, us. And so the question is why anyone should trust us. We are an independent research lab, so that might be one reason to trust us, but that's clearly a potential problem. And there's also a single point of failure because it's centralized, but it's very important to emphasize that we don't want to replace the existing PKI and code signing infrastructure, but we just want to extend it. So if our system is not available, we just fall back to the original system that we use today, so there's not a big loss. That's also very important that the database must be fed with new data all the time, because it has value only if it has fresh new data, new signed objects, and regularly update what we know about those objects. And this is work, and this has to be done, so it's a sort of a limitation. Users should also learn about ROSCO and be motivated to use it, because maybe the average user may not understand the difference between ROSCO and VirusTotal or Google Certificate Transparency or Windows Smart Screen Filter and so on. But we can explain this to users, of course. And signing parties should also learn about ROSCO and be motivated to use the system. And this is somehow related to the available amount of data. So the more data we have and the more accurate data we have, this is the better for signing parties to use our system. Okay, I will skip the related work because I'm over time. So future plans. First of all, we need more data in the database, so we continue crawling, of course. But we also are thinking of developing some collector applications, for instance, browser plugins, which would, whenever a user visits a website or whenever the user downloads some software to install, then this plugin would automatically, using the JSON interface of our system, could query our system what we know about this website or what we know about this downloaded software. So this would provide a useful service to the user, reputation about the things that he just downloaded. And that by this we also get some data, because the object, if we don't know the object could be uploaded to the database by the plugin. The same can work with mobile apps. So we can do the same on phones and tablets. So whenever a user would download a new application, this mobile app would check it in our database and upload if we don't know it. And we are also open to collaboration with security companies, antivirus companies. They already actually check a lot of things about downloaded applications, obviously. And they could, in fact, use our database to check this reputation information as well and provide some data to us. We also are thinking of building a Google Certificate Transparency monitoring system. Monitors there actually follow what are the new certificates that have been issued in the world, and in this way we can learn about all new certificates that have been issued. In the future we also want to use this database for searching interesting anomalies and computing interesting statistics about everything which is signed, and we also plan to open ROSCO for the public for non-commercial use. But actually, currently, if you are interested, so if the community is interested, then we invite you to try the system out. So if you go to the website, there is a registration button there, so you can register and get access to the system, or you can just send us a mail to this email address, rosco-vb2015@crisis.hu. And please, if you have any opinion, feedback, or comment, just send us a mail to rosco-feedback@crisis.hu. We want to know, your requirements, what new features you would like to have, how we should extend the system, how we should develop the system, because we really want to make it useful to the community. So any feedback is welcome, and we try to do our best to improve the system. Thank you for your attention.
So thanks a lot for your work. It was a quite interesting and especially impressive presentation of your work.
Thank you.
Unfortunately, we won't have time for questions, and I would like to remind you that the speaker's photo is right now in the green room.
Yeah. Well, I'm here for the afternoon as well, so if you just want to ask some questions, you are welcome. Thank you very much.
It was really impressive.
Thank you.